So grade 9th, we're into topic number 2 for the environmental chemistry unit. This one, as you can see on the side here, there is air and water quality, which we'll talk about this week, and then we'll talk about the some other stuff next week that goes into topic 2, like monitoring the atmosphere and things like that. But for right now, let's get into air and water quality, starting with water quality. A lot of this stuff we talked about last year, so it shouldn't be anything too crazy. You guys should be aware that the water you get to drink out of the tap has been treated. You probably would not be all that prone to drinking the water that is, flowing down the Wapiti River. But there are people in the world that do drink water very similar to that or worse. So as we kind of go through this topic, I want you to remember back, like last year, I played you that video of the boy who is completing his bucket list because kids in Africa, the average life expectancy is 5 or something crazy like that, or 1 in 5 kids die before the age of 5 in Africa. So there's a couple of things when we're measuring water quality. This isn't just for like making drinking water. This is for all different kinds of water quality. But microbial factors. So when we're looking at this, these are the teeny tiny things that live in the water, like bacteria, which for people in other parts of the world is the more common places where they will get themselves into trouble. There are bacteria that can cause all sorts of different diseases that can cause a lot of problems. I know friends of ours adopted a little guy, and when he got home, he had something called beaver fever, which someone will put it into the comments in the classroom, but it's a specific type of bacterial infection, I think, that causes problems with the intestinal tract. And I remember they basically had to treat his, when he arrived in Canada, they had to treat his diapers like biohazardous waste and dispose of them and not let anyone else touch them, and they had to wash their hands in a very specific way until the beaver fever is gone. And again, I have remembered what the thing is called now. It came to me just a second ago, but I'm curious if anyone in the class, first of all, is watching the videos. Second of all, if they can find out what that is called and put it into the comments. Aquatic invertebrates. So invertebrate means things that don't have spinal cords. So aquatic invertebrates are things that live in the water that maybe have a shell on them. So things like those little whatever swimmers, those striders that walk on top of the water, or anything else that lives in the water that does not have a spine. And again, the presence of those actually means that the aquatic ecosystem is healthy. So the more variety and the more quantity of them you have, then you will have better water than if you have very small numbers or very small diversity of those living things. Again, this is kind of getting us back to the biodiversity unit. There it is. So in the biodiversity, we talked about there being communities and populations and things like that. And so we're kind of back there again. So these guys are all aquatic invertebrates that live in a healthy ecosystem. Again, you might not want to go and drink this water, but it is actually a lot healthier water than if none of these guys are around. And there are actually measurable things, like they will know how much of different chemicals may be present, where it will affect some of these things, but not others. And so they can actually do a lot of science to go and figure out what's alive and how healthy the water or the aquatic ecosystem is. So there's a couple of other things that go into making aquatic environments healthy. One of them is pH. pH we talked about last one, which is like percentage of hydronium, which is how acidic or basic the water is. I remember from the last topics, from topic 1 that there is a scale from 0 to 14, and right in the middle at 7 is neutral pH, and so aquatic things can live in stuff down in the 6 range, but not much else will live below 6, and it will oftentimes kill those aquatic invertebrates that we were talking about above. One of the other things that is in there is dissolved oxygen content, which is right here. So that dissolved oxygen content is how much little particles of water. So you may know, if you guys are into fishing or anything like that, I know I like fishing out at Swan Lake on the Alberta side, and all throughout the year they actually have a pump that is sitting on the bottom of the lake, and they have a tube that goes to above ground at the lake, and they are constantly sucking in air and aerating the pond. That aeration actually allows for some of the bigger fish to survive better, so you can pull out some really nice big rainbow trout out of that lake, because the aquatic environment has lots of dissolved oxygen, which allows lots of those mayflies and those other things to live in the lake, and allows for a larger diversity of living things. So there's a lot of different things that are going to go into measuring is this aquatic ecosystem safe or healthy. Chemical factors, so there's dissolved oxygen and acidity or basicness, which is pH. The presence of heavy metals. Now this is not like metallic or anything like that. That is going to be things like dissolved mercury in the ecosystem. I'll put a video up just down here. There's a little blurb here about Minamata's disease, and so I'll put a video up connected to that, the dancing cats of Minamata. Plant nutrients, nitrogen and phosphorus. You guys who are Bear Lake people, you'll be familiar with this stuff as being the reason why you have algae blooms and makes Bear Lake borderline unswimmable, unless you want to go and wash off in the shower really thoroughly after you're done swimming in the lake. Pesticides, things that get rid of pests. Usually they don't apply them to the water necessarily, although I do know that some ponds, they will put in pesticides to try and control the population of mosquitoes. So that's one thing. And salts, oftentimes the reason why these salts may be in there is because of neutralization of acids. So if there is a acid like sodium hydroxide might be used to neutralize hydrochloric acid from rain clouds. Sulfuric acid, they may put magnesium in to react with sulfuric acid to create magnesium sulfate. These are both salts. So there's lots of ways that those salts can get in there. But all these things here and all these bullets are indicators of healthy ecosystems, healthy aquatic ecosystems. And the way they measure these things oftentimes isn't in like you can't see the stuff, there's no piece of salt sitting there at the bottom of the lake that you can go and measure, but rather they're measuring them in what's called parts per million or parts per billion. So what that basically means when you think about parts per million is one drop in I think it's a swimming pool is a part per million. And so there is a nice calculation. Oh, here it is. 1 drop of food coloring in half a bathtub is about a part per million. 1 drop of food coloring in a swimming pool is about 1 part per billion. And 1 drop of food coloring in the amount you need to fill 1,000 swimming pools is about a part per trillion. And so some of these things, they actually have to measure in those smaller quantities, because what happens is some things are so toxic that at a part per trillion, they can cause serious disruption to the natural functioning of living things. So when we're talking about water of course being the universal solvent, which we learned about last year, and being great at working its way through a variety of different environments, through pores in aquifers and things like that. Water is able to move things around that you wouldn't think are movable. Last unit there was a blurb in there, or last topic there's a blurb in there about sanitary landfills. And so when you're thinking about that kind of stuff, some of the stuff that may be in those landfills, if it leaches into the water table, it can cause problems at the parts per trillion level. Think about parts per million. Dissolved oxygen. So this is I talked about that lake where they would mix, or they had the pump to pump air into it to aerate the lake. If you have a fish pond, you guys are probably doing that. If it's connected to a river, that especially like this one has lots of rapids, what happens is the rapids actually, as they go over, they're mixing oxygen in at a very small, minute level. Now, most of the big bubbles will settle out, but it does create a more diversity in the water around the mouth where that river flows into the lake or whatever the aquatic ecosystem is. Now, if the lake is moving if the river is moving too fast like this one is, not many things can live in something that is this fast. But where this meets a lake, there will be life and abundant life. So if at 8 parts per million of oxygen, you have a large number of diverse invertebrates. At 6 parts per million, these guys begin to disappear. At 4 parts per million, these guys begin to disappear. And at 2, only the midge larvae and some worms can survive at 2 parts per million of dissolved oxygen. So oxygen is a really important piece, and that's why that lake, like Swan Lake will have that oxygen pump so that it can get up here, because then it has lots of invertebrates, which allows for those big fish to be caught in that lake. All right, scrolling. Phosphorus and nitrogen content. Phosphorus, so this is kind of what we're talking about with Poor Bear Lake. There is a huge bloom of these plants because these plants love the phosphorus and nitrogen that's present in these fertilizers or in the feces of the animals, and they begin to grow and grow rapidly. And what happens is they actually begin to take the oxygen out of the water. Where is it? So they use up too much dissolved oxygen in the water. The lake is no longer a place where fish and insects can survive. So these guys here cause problems because they still need water and bacteria to do their thing. The bacteria grows, and then the oxygen is not there for the other stuff that needs it. Like these guys here need oxygen to survive. But these guys don't need a ton. Bacteria steals it all and kills everything. Acidity, which we're talking about, pH. I already talked about that a bit. One thing I didn't talk about is right here, this spring acid shock. What can happen in an environment, especially if we don't have a ton of this around Alberta, but if you are in an area that has really high industrial activity, lots of factories that are pumping out various different things into the atmosphere around it. Just downwind from there, you'll oftentimes have acid rain that'll fall in the summer, but in the wintertime, there'll be acid snow. And then in the springtime, when that snow begins to melt, it actually will shock the ecosystem. It'll dramatically change the pH balance of that lake, and it will kill off all those things that are trying to get a start in spring, making that lake what's called a dead lake. So this is a problem in springtime, which is why spring acid shock. Pesticides, I think that's pretty commonplace for you guys. You guys should know about what pesticides are. We talked about them last year, DDT, a little bit this year even. But the one thing you need to remember with these guys is that as you go further up the food chain, you will have higher quantities. That's called biomagnification or bioaccumulation. And so the animals at the bottom of the food chain may carry only 1 part, but if this ladybug eats 10 to 15 aphids, and each of these aphids carried 1 little part of whatever the chemical was that's the bad thing, this guy, if he eats 10 to 15 of them, will have 10 to 15 parts of that toxin in them. And then whatever eats that ladybug is probably not going to stop at eating just 1 ladybug, but will probably eat 10 to 15 of those. And then you will have that, let's say a bird eats ladybugs, those ladybugs, that bird will now have anywhere from 100 to, I don't know what 15 times 15 is off the top of my head, somewhere in the 200 range, parts of that of that, whatever the chemical is. So toxicity goes up the food chain and magnifies as you get closer to the top. Now, LD50, I'll put a video on about LD50, this guy right here. LD50 just basically means LD is lethal dose, and 50 means 50% of the population. So what amount of a toxin will kill 50% of the population? And for some substances, it is absurdly low. Other substances, it is significantly higher. This is a measurement that we actually use for all known chemicals when we're thinking about it getting into the ecosystem. How much of it in the ecosystem would kill half the population? And this over here, just really quickly, the poor rat, he is the scapegoat of all this. He is the one that ends up being the bearer of all the bad news, because he is the one that we test these things on. So we take a rat and we say, if we introduce this amount of, in this case, table salt, or down here DDT, we are putting that amount into rats, and we're seeing how much, what quantity in milligrams or micrograms in some cases does it take to kill half the rats in the test population. So heavy metals, again, I said I would put a video on about Minamoto's disease. This is a really serious disease that affects an area in Japan because of mercury poisoning, and that Minamoto disease is a really unique thing. Again, it's very cool science, very sad for the people that are hurt by it. And that brings us to an end of our video on topic 2.1. So I will put those extra videos on there. Watch those, they're really interesting, and then there'll be questions at the end of topic 2 for you guys to do.